Hi everyone, I'm going to now do a quick worked question. We've been given the third Legendre polynomial, 5x cubed minus 3x over 2, and we've been asked to show that it's orthogonal over minus 1 to 1 to each polynomial of degree 2 or less. Let's start by highlighting our important information. We have got our lower limit and our upper limit, and we have got a polynomial over here. Now, what's also important to remember is they're asking to show that it's orthogonal. We know, according to inner product space, that if it's going to be orthogonal, then our inner product needs to be equal to 0, such that we will. Let's consider a polynomial of degree 2 or less. So let's let that polynomial be L of x. If we want it to be a random or arbitrary polynomial, we can state that it's going to be ax squared plus bx plus c. That is our polynomial. We want to make sure that our inner product or dot product, essentially, if we're thinking in that regard, if we want to make sure that it's going to be 0 for orthogonality, we're going to be considering, let's put in our limit, so minus 1 to 1. Let's put in our f of x. So I'm going to put in p3 of x, and we're going to be putting in our lx. So let's just color that one as well. So we're going to do this. We're going to make that purple. So p3 L of x. And let's close it up with dx. So we want to make sure that we're wanting to test to show it's orthogonal. We need that to equal 0. So that essentially is our objective. So if we were to substitute the two equations that we've got above into that, so the 5x cubed minus 3x over 2 for the p3 and the ax squared plus bx plus c, we would land up with integral from minus 1 to 1. Then we will land up with our p3, which is going to be 5x cubed minus 3x over 2. And then we're going to have our lx, which is going to be ax squared plus bx plus c. And we'll close that up with a dx. We then start multiplying this out. Let's pull out some common factors to begin with to make it easier. So pull out a half. We're still going to be going from minus 1 through to 1. And because we're multiplying it out, I'm going to change back to black. We now land up with, pulled the half out. So we land up with 5 ax to the 5. Let me make that clearer. 5ax to the 5 minus 3 ax cubed plus 5b x to the 4 minus 3bx squared plus 5 c x cubed. Let me make that clearer again. Cx cubed. 5 6 cx cubed minus 3 cx dx. We can simplify this a bit further as well. Let's categorize according to which x term we have. So again, we've got our half on the outside. We've got the integral from minus 1 to 1. And we're going to start organizing this in terms of x, powers of x. So we have 5a x to the 5. Our next term is x to the 4, so we're going to have plus 5b x to the 4. Now we've got multiple x to the 3 terms, so we're going to land up going plus, we've got our x to the 3, we've got a 5c for this term, and we've got a minus 3a x to the 3. And then let's look at our x to the 2 terms. We only have 1 minus 3b x to the 2, and then we've got 1 x term. So we finally end off with minus 3cx dx. And let's double check we've covered them all. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. And this one, we group 2 together, so that's going to be our 6th. Now, the nice part to remember is because we're integrating from -1 to 1, we can eliminate all of our odd terms. So what that means is if you integrate x from -1 to 1, you're going to land up with a 0 value. So that we can say is 0. We can say this whole term is going to equal 0, and we can say that this whole term is going to equal 0. Because whenever you're integrating just the independent x to the power of an odd number term, it'll go towards 0. So with that in mind, let's rewrite this. We've eliminated those, so we still have from our -1 through to 1. But inside we are now left with 5bx to the 4 minus 3bx to the 2 dx. Now what we can also see, we can pull the factor of b out if we want, but I'm going to just do that involved in the next process. So we would land up with b over 2, and 5x to the 4, if we integrate, we increase the number, pull the number into the denominator, that'll cancel with the 5. So we land up with x to the 5 minus, again, exactly the same thing happens here. We'll have a 3 which goes into the denominator, minus x to the 3. Now remember, we are working with limits from -1 through to 1. And these are odd terms, so we know that we're going to, the positive and negative limits of it are going to be the same as each other. But because we're working from -1 to 1, what we're left with is something which is going to cancel each other out, because 1 to the power of 5 minus 1 to the power of 5 is 0, and -1 to the power of 5 minus -1 to the power of 3 is 0. So what we can then see is if we were to solve that out, we would get 0. Because we get 0, we can therefore conclude it is orthogonal. It's orthogonal to all polynomials of degree 2. Is it 2? No, I think it was 3. Of degree 2 or less. 2 or less. So that's the first question I wanted to cover. It's quite a simple question, but it follows a lot of the key principles and helps to reinforce understanding. The next question I want to cover, I won't do it in another video. Let me just do it here. So we've been asked to apply the Gauss-Legendre using n equals 2. So let's go apply Gauss-Legendre. N equals 2. That's what we've been told. To the equation from -1 to 1 of 1 over 1 plus t squared dt. And we've been told to compare it with the actual value, which we've been told is pi by 2. First thing we need to check are our limits, and we can see our limits here are -1 to 1, which is perfect. So we don't need to touch our limits. We also know that our P2 equation, P2 of x, is equal to 3x squared minus 1 over 2. That is a given. It should be a known value either from your textbook, or if you do things on campus, you will have it in a formula sheet. Now, because our bounds don't need modification, we can skip the modification of bounds. With the P2, we also know that we saw earlier, our C1 is going to be equal to 1, and our C2 is equal to 1, and our X1 is equal to 1 over minus root 3, and our X2 is equal to 1 over root 3. These values over here we've already derived earlier from that equation. So now we are done with this equation. We don't need to look at it anymore. What we need to now consider is our different function values. So remember, we had f of x1 and we had f of x2. So let's consider f of x1. So in this case, we're looking at t. So we have our equation 1 over 1 plus t squared. So f of x1, I'm calling it x because I've already written it like that. So 1 over 1 plus, I'm going to go x1 squared, which is going to be, if we substitute that in, we have 1 over 1 plus 1 over minus root 3 squared. You work that out, it should come out to 3 over 4. And over here, 1 over 1 plus x2 squared. Exactly the same because it's squared, we know it's going to come out to 3 over 4. Therefore, we also already have our C1 and C2 values, so we apply our what we found earlier. We have minus 1 to 1, 1 over 1 plus t squared dt. And we are going to be, it's going to be approximately equal to C1 f of, I'm going to put it T1 plus C2 f of T2. And we can already see C1 is 1, C2 is 1, f of x1 or T1. So let me make this a T. F of T1 is 3 over 4, f of T2 is 3 over 4, so we have 3 over 4 plus 3 over 4, and we know that that is going to be 3 over 2. Now, the final part of the question, they have asked us to compare that to the actual value. So if we go compare to actual value, and we've been told the actual value of the integral is pi by 2. So our exact error formula is going to be equal to E is the absolute value of the known value, which is pi by 2, minus the determined value, which is 3 over 2. And if you punch that into a calculator, you will find that we come out with 0.07080. And that is your exact error. I hope that helps. Good luck with all your work, and I will put together another video soon.